Right. So the other possibility is if it's vertically oriented, then depending on the depth or the height of the object, you'd have a different amount of force applied to that object. Right. So what we would want is the cumulative exertion of force upon the object, but that would depend on the different level in terms of height or depth. All right. Now, there's also oblique orientations, but we're not going to get into that because that's a little bit more complicated. All right. I found a nice video explanation when I was first learning this. I needed some resources, and this is where I went. So, if you don't like my explanation, then maybe this would be a place for you. All right. So, the first example is the case, the simpler case, which is uniform uh, depth. So find the fluid force on a rectangular metal sheet measuring 3 by 4 that's submerged horizontally in 6 feet of water. All right. So we know, again, we're looking for fluid force. So F equals PA. All right. Now, again, P is defined as WH. So F is equal to WHA. All right, so W again is the weight density. It said water, so 62.4 given. All right, now they're in pounds per square foot. So we want to keep that in mind. So pounds per square foot. The height or depth, 6 feet of water. And the area, 3 by 4, is 12 square feet. All right, so that's our area. All right, so feet squared cancel. And so we're just looking at the product of these measures. So 62.4, oops, times 6 times 12, so times 72, is going to be 4492.8. And that's, well, the only things that are left are feet and pounds. So that would be our units, foot-pounds. Easy case. Now, if we have a situation in which the object is submerged vertically, it gets a lot more complicated. So that's what we're going to tackle now. All right. So we have the information here, but I'm going to just kind of walk you through it on the next page. So page 47. All right. So find the fluid force on a rectangular metal sheet measuring 5 feet deep by 1 foot wide that's submerged vertically such that the topmost point is 1 foot below the surface of the water. All right, so I'm going to draw a diagram here. So X and Y axes. It's rectangular. It's 5 feet deep by 1 foot wide. So I'm going to draw something that looks along the lines of those dimensions. All right, the topmost point is 1 foot below the surface of the water. So I'll make this the surface of the water. So that's at 6 feet. All right. So what we're going to do is kind of sort of apply something very similar to what we did with volumes of revolution, except we're not revolving around an axis. What we want to have is some location that we know relative to the surface of the water. All right. So what I'm going to do is I'm going to create an arbitrary rectangle that's on the piece of sheet metal. All right. And so we're looking for, if you remember in the previous page, it was, F equals PA, but ultimately it ended up being WHA. All right. By making all the appropriate substitutions and all that good stuff, that's where we ended up. All right. So weight density times height times area. All right. So again, if I just bring it back, we had WH giving you the pressure, and then popped into this formula for P. The WH got multiplied by the A, and then that's where we ended up. All right. It was all computational, but now it's going to be integral. All right. So the area, when we're talking about the area, we're talking specifically about the area of the arbitrary rectangle. And that arbitrary rectangle has two dimensions. One dimension is the same kind of thickness that we've been using for volumes of revolution. In this case, it would be a dy. Its length, it happens to be constant, but let's keep it general for a second. It's the distance from the y-axis, horizontal distance from the y-axis to some point in space, which we call x. The weight density, it is water. So that's 62.4. So again, that's not magic. That's just coming from the table here. That information needs to be given to you. It's not the focus of this course for you to memorize weight densities. So on a test or any other kind of assessment, that would be given to you. All right, so don't worry about that. Sometimes I even put it right in to the equation, as part of a multiple choice question or something like that. All right, so height, or h, represents height or depth below the surface of the water. So that's going to be this measure, which we don't know. But I do know this measure, because if I'm defining this as the x-axis, when I'm talking about the vertical distance from the x-axis to a point in space, also known as y, and we know the total distance from the x-axis to the surface of the water is 6. Oh, that just doesn't want to draw straight. That's going to give us a height of 6 minus y. The area is x multiplied area of the arbitrary rectangle, whose location will change depending on whatever y is. But since the x value is uniform, the area of that arbitrary rectangle is going to remain constant, which is nice. Doesn't always happen, but when it does, it's nice. So x times dy. All right, so the dy is the key to determining the bounds. So when I set up my integral here, my bounds have to be y bounds. I think about where this rectangular metal sheet begins and where it ends. So it begins here at 0, it ends here at 5 in terms of y. So I got my 62.4, I have my 6 minus y. X I need to swap out because this is an integral that's defined in terms of y. Once I have that, I'll be in good shape. So I would ask myself, okay, well, what is x? Well, in this case, x is equal to 1. It never changes. All right, so that's actually kind of nice. the x value that defines this distance here, since it goes to any point that's on this line, that line has an equation of x equals 1. All right, so then we're in pretty good shape. So math 9, 0 to 5, 62.4, 6 minus y. You use x if you want, as long as you're consistent. And you get 1092. Right. And the units are consistent with the stuff on the previous page, feet, and the 62.4 was a measure of weight density that I gave in pounds per square feet, or per square foot. So these are going to be foot pounds. All right. Number 9, the vertical gate in a dam has the shape of an isosceles trapezoid, 8 feet across the top, 6 feet across the bottom. We'll start there. All right, 8 feet across the top, 6 feet across the bottom. It's not perfect, but it's the best I can do. It has a height of 5 feet. We want to know the fluid force on the gate if the top of the gate is 4 feet below the surface of the water. All right. So what we're going to do is overlay this upon a set of coordinate axes. Okay, I think that's fine. I can grab that. I'm going to put the axes right smack dab in the middle. I don't really care about the left-hand side because I could just figure out the right-hand side and double it. So I'm going to do something like this. It says the top is 4 feet below the surface of the water. It's 5 feet in height. Oop, that's a little thick now. So it gets up to 9. And again, it was 8 across the top of the longer of the two bases of your isosceles trapezoid had a length of 8, and the shorter one had a length of 6. So its half length would be 4 and 3, or each half length. All right, so that gives me a coordinate here of 3, 0, and a coordinate here. I'm going up over 4, up 5. The reason that's important is because if I draw an arbitrary rectangle in here, it's not going to be constant anymore. If I can get a rectangle to be drawn. All right, so we know our thickness is going to be a y thickness, dy. The length is going to be x. Some horizontal distance from the y-axis is known as x. That part is all fine. What we don't know is what x is in terms of y. All right, but we do have a linear relation here So what I'll do is I'll write the equation of a line. Alright, so y equals m times x minus h plus k. So h and k is a point on the line. I like the 3, 0. M is the slope. So 5 minus 0 over 4 minus 3. So we're talking 5 times x minus 3 plus 0. Simplify. Y equals 5 times x minus 3, or 5x minus 15, either way. I would just do a quick double check to make sure that everything kind of pans out the right way. If I plug in a 4 for x, 4 minus 3 is 1, times 5 is 5, so then that would be good to go. All right. Now, if I set up my integral here, I'd be setting it up with bounds of 0 to 5. It's water, so 62.4. All right, so that's the weight density. The height, I'd be going to the center of any arbitrary rectangle, or really just to the arbitrary rectangle, which has a height of y off of the x-axis. So 9 minus y would get us the depth from the surface, so that part's fine. So then the length x multiplied by dy is what I would need. Well, I have a relation here that's solved for y. In terms of x, I want to go the other way, so let me divide both sides by 5. Oops. And then add 3. And we would have the relation that we need. So y over 5 plus 3. And that's what goes into the calculator. All right. So it's really just a matter of, there's so many similarities, it's just a matter of finding the slight differences. So from 0 to 5, 62.4 times 9 minus y times, well, it's 1/5 y, so already there's 0.2 for the 1/5 y plus 3. Close it up, pop in a y, and so you get that number, but that's only half of it. All right, so I got to double it, and when I do that, so times 2, I'm going to get approximately exactly 13,936, again, foot-pounds. All right. So then last up, plate in the form of an isosceles triangle has a base of 5 feet and a height of 6 feet. All right, so base of 5, all right, height of 6. So we could do the same idea, split it. It's submerged, vertex down, all that good stuff. So we could draw the isosceles triangle. All right, 2 feet below the surface of the water. So I'll just kind of rough it out here. So again, they said base of 5. So that means its half base is going to be 2.5. And a height, I already forgot, 6. I've said it like 6 times, but I already forgot. And so 2.5 comma 6 is one of the coordinates. The other one, and it does appear to be linear again, is 0, 0, so that's good news. Now, again, it's 2 feet under the surface of the water. So that's going to get us up to 8. Actually make that look like an 8. How about that? How about that? Kinda. So my arbitrary rectangle again is going to have a thickness dy, a length of x, its distance below the surface is going to be related to its distance above the x-axis. Distance above the x-axis is y. Distance below the surface would then be 8 minus y. Right. Now, that length, we can go a couple of different ways here. We could actually find the difference between two equations. Because it's isosceles, one of them is going to have, it's basically an absolute value function, where you're going to have a positive slope and a negative counterpart to that slope. Or we could do what we did before and just double it. Either way. So we know this maxes out of the 6. So 2 from 0 to 6, 62.4. And still water, so that makes sense. 8 minus y. And we need the equation of this line. So the slope is 6 minus 0 over 2.5 minus 0. So 6 divided by 5 halves is going to be 12 fifths. Alright, so again, y equals m times x minus h plus k, where h and k represent a point on the graph. I think it would be very nice to use 0, 0 as that point on the graph. So y would be equal to 12 over 5x, which means that x is equal to 5 over 12y. And then we have our dy. Alright, so we can crunch that. So 2, math 9, from 0 to 6, 62.4 times 8 minus y. That's not an 8. Times 8 minus y. Times 5 twelfths. Times y. Close it up. Throw on a y at the end. That's not a y. I keep doing that. And we get 3744.